social swarming applications. The speaker will be Peter Pelacki from City University of New York.
Thank you. So this was a joint effort between us from the City University of New York and Tel Aviv University and the University of Southern California. So again, the title is Timely Report Delivery and Social Swarming Applications. So in social swarming applications, reporters are equipped with smartphones that are in the field, and they are to report on certain events to an internet-connected central authority, which we call a commander. So with the penetration of smartphones nowadays, many operations like search and rescue or coordinated firefighting increasingly use social swarming to obtain situational awareness. One such instance was the DARPA Balloon Hunt Challenge, in which several teams participated, and we had mobile users coordinated to locate balloons as part of the grand challenge. So all these are examples known as collaborative social swarming, where teams of people collaborate to perform on a well-defined task. So our task that we're interested in is going to be timely report delivery. So each reporter has a smartphone, again, with a 3G and Wi-Fi interface. So the reporter is to transmit a created report. So the first thing he does is creates a report. It has a certain size. He wants to transmit this report on time to a commander through a 3G interface. Wi-Fi is not available to connect to the commander. Each reporter has a deadline which is set by the commander, by which he must transmit his report by. And what we do is we enable peer assistance through Wi-Fi. So a reporter can assist another reporter if his file size is really large. So what can happen is the report can be broken up into several pieces, and those pieces can be transmitted to other phones through Wi-Fi, which is a lot faster, and therefore a report can be uploaded this way with peer assistance. So multiple helpers helping transmit a file up to a commander. And again, so this transmission is done to the commander through 3G, and assistance is done through Wi-Fi. And the objective is to maximize the number of timely reports, so maximize the number of reports that are transmitted on time, or you can associate a profit to each of the reports, so you might want to maximize the total profit received from the reports. Some kind of weighting. So more formally, you have end reporters, where reporter I has created a report. Okay, maybe he has some tasks, he has to kind of create a video, or a text message, or an audio clip, and it has size FI, and needs to be delivered to a commander by deadline DI. So again, each reporter is equipped with 2 radios, a 3G cellular radio, and a Wi-Fi radio for assistance. And now 3G has lower nominal upload speeds than Wi-Fi. So what we do is we normalize the rate to 1 per time unit, which means that if a reporter is looking to transmit a file of size FI, it'll take FI units of time. And the nominal Wi-Fi transmission rate between reporters has been noted by rho, and it's larger than 1, which is the 3G rate. So it's faster to transmit through Wi-Fi. So again, in order to help transmit the reports, these reports are broken up into segments. So reports are broken up by the reporter's phone, and this broken up piece is called the report segment. And now there are 2 delays which happen, so this doesn't happen instantaneously, obviously. So there's a fixed connection delay, which is called delta, and a transmission latency delay. which is proportional to the file size that's being transmitted. So if you want to transmit a file of size F, you need to weight alpha F time units, and take the ceiling. So, we have a couple different delay models, and we're going to explore three different types. The first is no delay. So assume alpha equals delta equals 0. In other words, there's no delay. So this is the same as all the reporters having all the files before time begins. So we'll call this the no delay model, and we'll see we have a optimal polynomial time algorithm which solves this. And then we have the one-sided delay model, and this approximates what's possible in today's mobile OSs. So what happens here is that the sender cannot, if he's sending to a reporter to help him, he cannot transmit the commander while he's doing this. So, and there's also a bit of a delay that's incurred. We'll get into it later. And then the two-sided delay model, both the sender and receiver cannot receive or transmit anything else while they're exchanging files, or while one is sending a file to another. Okay, so in the no delay model, again, we assume there's no delay, and we can show that this problem is computationally equivalent to a scheduling problem known as single machine scheduling that maximizes non-tardy job weights, also known as non-tardy scheduling. So in non-tardy scheduling, the input consists of a list of jobs, where each job has a processing time Fi, a deadline Di, and a profit Pi, and the goal is to find a single machine schedule that maximizes the weight of the non-tardy jobs. And the results from our non-tardy scheduling is known to be NP-hard. It has FP-TOS, and it can be solved in polynomial time if the weights are agreeable. What does that mean? That means if Fi is greater than or equal to Fj, where then Pi is less than or equal to Pj. So the same, because they're computationally equivalent, the same holds for TRD with no delays. So let's take a look at the polynomial time algorithm, which solves TRD, which is the one that solves non-tardy scheduling. It's known as EDF, earliest deadline first. So again, the model here is just to remind you, reports can be broken up into pieces. Everybody has all the reports in their pieces, and the question is, we wish to maximize the number of on-time reports. So the algorithm for solving this is to pre-process the reports according to the earliest deadline first rule to find the optimal set of jobs. So the first thing we want to do is determine which set of jobs are feasible or schedulable. This is our optimal set of jobs. And then, and then we schedule them. So reports are pre-processed one by one. All reporters assist in transmitting the next due report. This is the reason it's called earliest deadline first. So what happens is all the reporters transmit the first due report that's feasible. So all the computational power is going to go into transmitting that first report until it's transmitted, and then we move on to the next feasible report, and so on and so forth. But first, again, we have to determine what the feasible set of reports are, and that's the first part. That's the pre-processing. Once we have that, the whole everybody's processor goes into transmitting that first due report. Now again, if it is calculated, the next due report cannot be transmitted on time. Okay, so to determine the set of feasible jobs, which we do is we attempt to schedule the first job. If it can be scheduled on time, okay, we add that into our feasible set. We attempt to schedule the next job assume it can't be scheduled, what we do is we throw away the largest job encountered so far. So we throw away, say the first job was larger than the second, we throw away that first job, and we schedule all of the second, which is smaller. Now this job, because the first was scheduled on time, and it's larger and it appears first, the second one can definitely be scheduled on time. And we proceed in this manner to find a feasible set of jobs. So this is earliest deadline first. And then once we have a feasible schedule, we schedule the optimal set using earliest deadline first for everybody else to transmit the first report, then the second, so on and so forth. Now with delay, this is not going to be optimal. In fact, we'll see it's kind of far from optimal. We can actually show that TRD with delay, with the one-sided delay on the sender side, is strongly NP-hard for any alpha. Alpha is the proportionality of the delay, and delta. Delta is the constant factor of delay. And we can show that TRD with two-sided delay is even harder. Basically, it's hard already for fixed delay delta. And the reductions, they come from a well-known strongly NP-hard problem, three-partition. So three-partition, you're given a list of integers, A1 through AN. They're each between B over 4 to B over 2. And the sum of all those integers adds up to MB. And you have 3M of those integers. And the goal is to decide whether the list can be partitioned into M triples such that all have the same sum of B. So M triples of sum B. So we give a reduction from this problem. So clearly, again, the no delay model is an idealization. Wi-Fi connection establishment takes a non-trivial amount of time, and depending on channel conditions and data size, so can the data transfer. In practice, we actually developed a prototype of the system. TRD's pure assistance would be implemented either using Wi-Fi's ad hoc mode or infrastructure mode. We used infrastructure mode. Ad hoc mode leads to delays on both sides. Infrastructure mode leads to one-sided delay. So mobile OSs like iOS and Android fully support infrastructure mode, where a phone can act as an access point for a limited number of clients. However, when a phone is connected to a client, as a client to an AP, the OS, both Android and iOS, disables the 3G connection. So you can't concurrently transmit to the commander and also send the report segment to somebody else for help. Thus, if I assist J, it cannot concurrently use the 3G connection. So thus we assume the one-sided delay model for our experiments and also for our prototype. Okay, so we can show that TRD with one-sided delay is very hard to approximate. It's as hard to approximate as independent set. We can't hope for a constant factor approximation. So we give heuristics. So we developed two heuristics for TRD with one-sided delay. The first one's called IFG, iterative frame generation. So what we do for this heuristic is we split up the reports into two sets. The first set can transmit their reports on time. We figure since you can transmit your reports on time, there's no need to split up the reports and waste time. The second set needs help. So it can transmit part of its report, but it won't be able to finish the whole report on time. So the set I minus needs help. And what we do in IFG is we attempt to transfer parts of files to those that can help. And we do that using two rules. We fill in the longer QPs first. QPs are periods of time which are kind of not doing anything and can help. And for each QP among the corresponding reporting neighborhoods who are in I-, select a reporter whose RS has the earliest deadline. So we help those who have the earliest deadline, we help those guys first. So here's an example in the idealized setting. So this is an example of IFG in a no delay setting. It's not optimal no delay, but this is just a illustrative point. So what happens is we have a bunch of jobs. The jobs in I+ can help themselves. So jobs go from 1 to 7, they increase. So we have jobs which can't help themselves. This is a job in I- which can't help itself. This one can't help itself, so on and so forth. So what we do is we help those people that need help first. So we would help this guy first, and we would, both these phones would help this person, and then we help the next person, which is that guy, so we split reports and help him, and then we move on to the guy with the next deadline, so on and so forth. So this is IFG. And the last kind of graph there just shows that in the one delay setting, there has to be some kind of delay. So there's a delay before files can be transferred. So with IFG, there's something we also developed reverse IFG, which is a heuristic. Okay. Which is just kind of the reverse of IFG, meaning we help first and then we transmit a report second. So within RFG, a person's report is scheduled as late as possible within the frame. And so in other words, we try to help first and we assist our reports at the end. So we assist it, we transmit our reports so that kind of they come in just in time and we help first if we know we can help. Okay, so these are some simulation results. We have 2 minutes. So let me actually go into the prototype. We developed a prototype system on Android where the commander was implemented with JSP and Tomcat 6.0. The experiments were performed here in China by Benu using Google Nexus 1 phones with China Unicom WCDMA SIM cards running Android 2.43. And this was the implementation. So on the phone side, there was a phone application startup. We had to register with phone information to the commander. There was a neighborhood discovery phase. We also report the topology, meaning the report sizes, where, the location. Then the commander calculates the schedule with IFG and RFG. Then he broadcasts the schedule to all the reporters. And the reporter's job is then to divide the reports and do the scheduling. And then we send, and then the report is uploaded to the commander. And this was the kind of experiment environment we had. It was in an apartment, and there were 6 possible locations which phones were located. We used 3 phones were used in any of those 6 possible locations. And we give these results where just kind of quickly, the first graph is the speed-up ratio, meaning how much faster reports were uploaded with IFG and RFG versus just with everybody transmitting to the commander. And we had 3 test experiments. And the second was the completion rate. What percentage of the reports were completed? Notice RFG kind of falls off here. Why? Because in RFG, a person uploads his report at the end, and this caused certain reports to miss their not coming on time. So that's it. Thank you.
Time for one quick question. Quick question from the audience? I have a question. I don't know if the two-sided delay version, what is the hardest for this strong
Strong NPR for just fixed delay, delta. Yeah,
So both 3 versions are all strong NPR.
yeah, and they're hard to approximate as well. It's hard to accurate.
can speak, okay? Thank you. The second presentation will be personal marks and community certificate detecting clones in wireless mobile social networks. It will be presented by Marco Valerio Alpera. He's from Sapienza University of Rome.
Hello everybody. I'm Marco Alpera. I'm a PhD student at Sapienza University of Rome. My advisor is Alessandro Maic. And today I'm going to talk to you about this work. So this is not working. So this is the outline of the paper. I will start by introducing the problem, then I will talk about my system, the interpretation. I will show some experimental results, and then we can finish with some concluding remarks. So I'll talk to you about a little story, because maybe this is going to make the presentation easier to follow and more unusual presentation. So this is Bob, and this is his smartphone. So not everybody asks Bob uses his smartphone not only to make phone calls, but also to perform many other tasks on the internet. So for instance, Bob reads and writes emails on the Gmail app, he gets in touch with his friends using the Facebook app, he pulls the most important files from the cloud using sources like Dropbox, he maybe accesses also his bank account, and many of the services from the web. So for instance, he buys tickets online, he posts on forums, and so on. So again, like many of us, Bob is not going to type in his password every time he uses one of these services, but lets his smartphone to store all the passwords and keys that are necessary to use them, and try them in such a way that you can have the smoothest experience as possible. So, unfortunately, one day Bob goes to a pub and forgets his smartphone on the table. Of course, when he goes away after a few minutes, he realizes his phone is not in his pocket anymore, and so he runs back to the pub, hoping he can find his device. When he gets to the pub, he finds that his device is the same exact place where he found it, where he left it. So he feels really happy because he didn't lose his valuable device, and also feels safe because he thinks that nobody got access to the device. What happened, by the way, is that in the pub there was somebody, a little person, which we're going to call E, who decides to exploit the fact that Bob left his smartphone unattended for a few months. And so she made a whole copy of the memory of the smartphone in a new smartphone that's created a clone of Bob's smartphone. And this copy in particular has a copy of all the access keys that were stored in Bob's smartphone. So right now Alice is able to use these keys in order to access all these services here using Bob's identity. And what's worse is, and the worst part is that since Bob is not suspecting anything, he's not going to change or remove his passwords anytime soon. So he has a lot of time, he has a lot of time in order to use Bob's identity online. So she can read Bob's mail, she can get Bob's files, she can access the internet Bob's bank account, and so on and so forth. So what can we do for this kind of problem, which apparently is really destructive for the most common authentication mechanism we have nowadays. So we decided to use a new authentication mechanism, which is called which is based on social biometrics, and which are meaning that it's based on the characteristics that define us in a unique way from social point of view. And we call this authentication mechanism, we call this new certificates. And the bottom line is that in order to pretend to be Bob, that is in order to log in as Bob, we have to be like Bob from a social point of view. So let's see how it works. So this is Bob again, and this is all the people that Bob met during one day. So these people here with question marks on are just strangers, that is people that Bob doesn't know, and that he met just for any random reason, like for instance they were waiting at the same bus stop where Bob was. On the other hand, these people here in the circle are people that Bob is going to meet much more frequently than the other ones, because they belong to what we call Bob's community. That is, they are the people who define the social environment in which Bob lives. That is, these guys here might be Bob's colleagues, this guy here might be Bob's boss, this other guy's friends, this other guy here the other one his girlfriend, and so on. So since Bob met these people, his smartphone, which was sitting in his pocket, was able to sense the other smartphones of all the people around Bob in his community, using, for instance, a short-range radio like a Bluetooth radio. Now, community certificates allow Bob to receive continuously proofs about his social behavior. So these proofs are issued by the smartphone of the people in Bob's network, and are simple cryptographic objects which have which we're going to call, let's say, contact certificates, and that have the characteristics of having a validity which is limited in time. So what happens is that since Bob lives in his community, he's going to be able to receive constantly new and fresh contact certificates proving the sort of behavior from the people in his community. Now, what happens when Eve clones Bob's smartphone? So these contact certificates are going to be stored in Bob's smartphone. So Eve is gonna get a copy of these certificates too. But the problem is, the fact is that since Eve is different from Bob, she has a social behavior which is different from Bob. And so the contact certificate that she stole from Bob and that were related to Bob's community are going to expire. So basically, since community certificates require that a set of not expired contact certificates are provided during the authentication phase, Eve is not going to be able to use these services here using Bob's identity anymore because she has expired, the contact certificate that she stole are going to expire soon. So apparently this solves the problem because even if Bob doesn't suspect anything, Eve is not going to be able to use his identity online for long. However, this is not really the case because so far we have assumed that Eve's social behavior is quite different from the one that Bob has. That is, Eve is an outsider with respect to Bob's community, somebody who might not even know who Bob actually is. But it's still perfectly possible that Eve is actually somebody inside Bob's community, that she might be a friend of Bob, which is not really a friend because she tries to steal money from Bob, but still somebody in Bob's community. Or in an equivalent term, somebody who, an attacker who doesn't know Bob, but that is willing to spend time and effort in order to understand what Bob's community is, and in order to try to get in contact with this community and try to refresh the contact certificates that she copied from Bob in order to be able to use Bob's identity online. So of course, community certificates in this case it's not able to defend Bob, and so we have to complement it with another system which is called personal marks. And personal marks basically identifies if there is more than one people using Bob's identity inside Bob's community. So let's see how it works. So this is Eve, this is Alice, somebody in Bob's community. She might be Bob's boss or a colleague of Bob or a friend of or a colleague of Bob or a friend of Bob, and this is Bob. So when Bob meets Alice, community certificates allows Bob to receive a new contact certificate or contact proof from Alice. And this is the exact moment in time when the personal marks system kicks in. Because before Alice gives a new contact certificate to Bob, she's going to ask Bob for the previous contact certificate that she gave to Bob in such a way that she can check if the latest contact certificate that Bob has received from her is what she believes is the latest contact certificate that she gave to Bob. So since nothing bad happened yet, Bob is going to be able to give the latest contact certificate to Alice. Alice is going to perform a check. The check is going to be passed, and so she's going to give a new contact certificate to Bob. Now suppose that after a certain point in time, an attack happens. In this point in time here, this is a timeline, right? So right now in Bob's community, from this point in time on, there will be two people using Bob's identity. One will be Bob, of course, the honest person, and the other one will be Eve, who's going to pretend to be Bob in order to get fresh and new contact certificates from the people in the Bob's community. So now assume that without loss of any generality, that the first one to meet Alice in Bob's community is Eve dressed as Bob, because Eve now has all the access keys of Bob, so she can pretend she's Bob inside Bob's community. And so since the contents of the memory of the clone that Eve made are still the same of the one of those that are in Bob, she can simply ask ask Alice for a new contact certificate, and so because she can pass the test that Alice is gonna perform on the certificate that she gives her. So basically, Eve now is going to be able to get a new contact certificate, a new and fresher contact certificate with a longer expiration time with respect to the one that she had before. However, what happens is that since Alice is inside Bob's community, she's going to meet Bob very, very soon. So what happens is that when Bob is going to ask Alice a new contact certificate, that Alice is going to ask him first, because of personal marks, he's going to ask him first the previous contact certificate that she gave him. He's going to give her this contact certificate, which is not exactly the same one that the latest one, the latest contact certificate that Alice believes she gave to Bob, but it's the previous one. So right now, the test that Alice makes on this contact certificate is not going to pass. And so Alice is going to realize that there is at least one more person outside, together with Bob, that is using Bob's community. And so she's able to create a proof which is undeniable and which it can be broadcasted to all the community of Bob, and that will make it possible for the people in Bob's community to not trust Bob's identity anymore until Bob refreshes all his passwords and keys and certificates and so on. So, of course, the same thing would have happened if the real Bob was the first one to meet Alice, and then Eve, versus Bob, was the second to meet Alice. The same kind of reasoning applies. So right now we can see how personal marks and certificates were combined. So this is Bob, and this circle here is Bob's community, and this is Eve. So because of community certificates, Eve cannot just copy the contents of Bob's smartphone and run away from Bob's community, because otherwise the contact certificate that she stole, that she copied from Bob are going to expire, and she's not going to be able to use Bob's identity anymore. And so she's pushed inside Bob's community. However, because of personal marks, Eve gets in contact with Bob's community, she will be detected, and so Eve is pushed out of Bob's community, right? So this means that Eve is left with no choice but not getting in contact with Bob's community and letting the certificate that she stole from Bob, that she copied from Bob, expire. And so she's going to have only a limited amount of time with respect only a limited amount of time in order to use Bob's identity. So this is so in order to evaluate the system, we use 4 different data sets. So the first 3 data sets, which are dark mode, ECSD, and reality, have been selected in the past using real-life experiments in which usually people were given little devices which were able to sense the presence of other devices of the same kind around them. And these data sets have been widely used in the past in the community in order to understand, for instance, what are the basic properties of human social behavior. On the other hand, this simulator here, this 4th data set here has been generated with a simulator which is called Green, and which has been formally proved to be able to reproduce the same characteristics of these traces here. So before running the test, we use a training period which is about 2 weeks in order to detect which are the communities inside these data sets here and to tune the system. So let's see now the results. So this plot here shows what is the performance of community certificate system to detect to fight against outsider hackers. And so basically this is the CCDF of the average detection time of outsider, or better, the average time it takes for the certificates that the attacker steals copies from the victim to expire. So basically what we have is that with the twin simulator we were able to get that for the almost 90% of the cases it takes at most half a day for these certificates to expire. Whereas for the dark mode data set it takes in the 80% of the cases it takes around 1 day. It takes something like between 1 day and 1.5 days at most. Whereas for the reality and and DCSC traces, it takes for 80% of the cases 1 day and a half, and for the rest of the cases a little bit more time. So, and for what concerns, on the other hand, the ability of the system to detect insiders, this is another plot showing the CC depth of the detection time of insiders, that is, the time it takes for the system to detect an attacker who tries to get in contact with the victim's community in order to get new contact certificates and fresh contact certificates. And so, basically, we got that for the Dartmouth and string traces, we had that in let's say 90% of the cases, something a little bit more than 1 day at most in order to detect an insider, whereas for the reality and USC traces, it takes in 80% of the cases about 2 days and a half. So the reason why usually reality and USC traces they have worse results with respect to Dartmouth and string traces is that, as I shown at the beginning of this section, these traces are have a much smaller number of nodes with respect to the other traces, and so their social dynamics are much lower with respect to the other traces. So, as conclusion, personal marks and community certificates is an authentication mechanism that protects against powerful attacks such as identity theft, such as the fact that Eve is using DOS community public author identity 9, is resistant to forgery because it's a distributed system. That is, Eve, when Eve cannot forge herself the contact certificate that she needs in order to use DOS identity 9, and it's user-friendly. It's user-friendly because it's transparent to the user, and because the user doesn't have anything more to do rather than just live his life and get in contact with the people he usually get in contact. So as a future work, we are trying to handle the fact that an attacker might decide to use a coordinated attack in which it clones not only Bob's device, but also all the devices of all the people in Bob's community in such a way that the attacker can try to generate the certificate by himself, the certificate that is gonna need to use Bob's identity online. And also we want to leverage spatial reality because we want to exploit the fact that people not only goes more often with the people along with the people in this community, but also goes quite often in the same places, like the workplace, like the university, or the same club. And we are currently working on an implementation of real devices, which is gonna show what are the performances of the system on real cases, in which we have a wider knowledge of the social behavior of the people. And so that's it.
And what happens if, for instance, Bob travels to China for a conference 1 week?
Yeah, this is what I want to.
His life changes for a while.
Yeah, this is what I want to talk maybe, but I don't know if I have enough time. So basically, you can use different profiles. So you can say something like, okay, Bob is somebody who lives in 2 very different communities. So maybe it's somebody who works in a city for in the weekdays and lives in a totally different city in the weekends, which might happen. So in this case, you can have different profiles and say, okay, when it's weekend, the community of Bob is this set of people here, whereas when it's another time, weekday, for instance, the community of Bob is another people. So in this way, you can have similar results to what we get. Right?
Some questions? I have a small comment. I'm wondering if the frequent location information will help to detect the clone.
Sorry.
The frequent location information.
No, I don't need it.
The frequent location, when people want to browse some information, they have their frequent location right. They have a stay in the office or stay.
Yeah, no, it doesn't matter. This system is until this moment, this system doesn't care about location. Because supposedly, if you go in your office, you're gonna meet your colleagues. If you go at the pub, you're gonna probably go there with friends. So it's gonna work. For sure, you can improve the system by also using the patients because maybe Bob sometimes goes alone at home and nobody's there, so you can use maybe his Wi-Fi device, sorry, Wi-Fi router in order to prove that it has been at home and so on.
Thanks, speaker. The third speaker is Yun Xiafeng. She's from Qingdao University of Science and Technology, and she will present a mobile terminal-based trajectory preserving strategy for continuous query FES users.
I'm now working in Studio IT, and I used to work in University. This work is part of our work in our team. So some of the results are done in the Hangzhou city. Here is the content of my presentation. First, in nowadays, location-based services is not popular, and in most these systems, in order to enjoy one location-based service, some messages contained in the message sent by a user should include his current location information, but without safeguards, these query messages may pose a severe privacy risk, exposing users to constant application and tracking throughout the day. So, for our location-based service users, real-time application of location or trajectory is essential. Nowadays, many studies have been to achieve to protect location or trajectory. Now, shortcomings of current approaches may be most of them are central methods, they are complicated, so most of them can't be implemented on mobile terminals, and most of them need a third-party server to implement. Here is an example of current resolutions to provide location or trajectory preservation. The conductors are three tiers in the system, and here is the location-based server, and this is a third-party complicated location or trajectory analyzation server, and the users may use one or some of the terminals to communicate to the RBS server by the relay of the location analysis server. We can see that the users do nothing to their location or trajectory preservation. We have studied the problem of mobile terminal-based trajectory preserving for continuous queries users in the BI systems. Our goal is to protect users from being tracked by linking the user with his trajectory information without the third-party location analysis server. So here is the architecture we consider in the RBS systems. Now here is the RBS server, and here is the terminal of users. They may send their messages via the wireless AP to the wired router and relay in the internet to the RBS server in the internet. So there are three main components in our systems. there's no third location or trajectory preservation servers. We have several assumptions on the system. First, for the system, there's no third-party server to provide privacy anonymity, and users send location-related queries periodically to RBS servers, and these communications are relayed by API wired routers. Communication links, we assume that the communication links are safe. They are that is, we think the links we send messages to the RBS server are safe, so we mainly consider the problem of the data preservation in the RBS server. For the attacker, we assume that the attacker can only access data from the RBS server consistently, and they may achieve all communication data from the server. And they also can deduce location or trajectory of the user by analyzing the spatial time relationships between the communication records of users. The main idea behind waiter is quite simple. We try to make users send their queries to the RBS server with several fake queries, and these fake queries are selected and scheduled carefully so that multiple reliable trajectories are achieved from the viewpoint of a third party. Now, here is an easy example to show our idea. Suppose that the user starts from the point S and his true destination is D. In the waiter, we plan several passes to the destination. The point in red, DE and D1 and D2 are fake destinations. Suppose that the true trajectory of the user is from S through 3, 6, 5, 9 to the destination D. But he sent following queries in the 4 phases. In phase 1, he sent point 1 and 2. In the second phase, he sent point 5, 3, 7, and in the third phase, he sent 4, 9, 6, and in the last phase, he sent D1, D5, 8, and D2. Here is the possible path established by the attacker in each phase after he achieved all these data. We can see that by sending several fake queries, we can establish several available paths, so the attacker can't identify which is the true trajectory of the users. But waiter phase is several challenges. One main reason is that the attacker may distinguish the noise data from true position data if they are chosen arbitrarily by analyzing spatial and temporal relationships among communication records. Thus, the trajectory is affected by multiple factors such as type of the trip proposed, the real-time traffic conditions, and some other factors. resolve the following problem. First is we should interrupt the spatial-temporal relationships among location data. They may include in both true queries and the fake queries. We should also consider the impact of several factors mentioned above, such as the type of query time, the vehicle, the trip purpose, real-time traffic condition. So we adopt two resolutions to resolve above question. The first, we adopt noisy location select strategy to form the fake path. The matrix to select noisy location to form the fake path should be the real and reachable in the map. We put forward 4 rows to select the noisy location. One is the public location near or within the marketable places. The second is the noisy location should be independent. And the third is the places with real-time traffic information should be the first. And the last is we may send redundant inquiries in the noisy location selection. The second strategy is to schedule the query. We adopt 2 roles. First is called the normal step scheduling strategy, and we put forward an algorithm to schedule the normal query. And here is the input. There are D, V, and delta T. The output T, it means the time period between 2 fake queries. And in the algorithm, we use several parameters, cursor, mu, P, delta T, and here both cursor and mu are used to adjust the value of V. They are used here to consider the impact of several other factors which may impact the time period between 2 fake queries. The second resolution strategy is the disordered scheduling strategy. We mentioned that in order to query, the query sequence of the users may be disordered purposely to interrupt the spatial or temporal relationships between communicated data. This rule is especially suitable when the virtual paths have intersections with true paths of the user, and second, when the path segments near intersections where there are multiple entrance and exit of alternative paths. The performance evaluation consists of 2 parts. First, we analyze the trajectory preservation degree. The evaluation metric is called TPD, that is trajectory preservation degree. It is denoted by the number of visible passes achieved from the viewpoint of the attacker. And here are 3 parameters in our evaluation algorithm. Here, PR is defined as the trajectory risk possibility faced by the user at time TC, and P is defined by this algorithm. And TPD is defined by this, and we can achieve the trajectory preserved degree. minimum of it is still more than 1, so we can prove that at any time TC, the candidate path of the user is more than 1, so its true trajectory is preserved. Secondly, we also do some experiments to prove our resolution. We implemented the weight awaiter in 2 modes. First, in the first mode, all virtual passes start at the same time, and in the second mode, the starting time of the virtual pass of every user are independent from each other. That is, we can start the virtual pass at any time during his trajectory. In our experiment, users are divided into 2 groups. In the first group, users do not adopt weight awaiter. These details achieved in this group are used as matched to find the candidate passes for a character. And in the second group, users adopt weight awaiter. We mainly consider the scenario where users keep moving. We don't consider the scenario where he stops at one place. In our experiments, we select candidate passes from 2 parties and the virtual from a digital map. In our experiment, every user uses 3 to 5 virtual paths in his trajectory. Here is a map we take in our experiment. Most of them are from our school here, and they made it to the different destination in the Hangzhou. And they here, P1, P2, and P3 denote the true trajectory of 3 users, and weight P1, weight P2, weight P3 denote the virtual path we take in the experiment. For ease of exhibition, in our experiments, these 6 passes are mixed in the passes of the 3 users. And here is we did not start point. The detailed path information of the 3 users are listed in this table. Here we just provide the result of 1 user. We mainly provide the relationships between the time and the distance of 2 queries. And here is the candidate trajectory of the between different time and distance of 1 user. From the result, we can see that the starting time of users impacts the average velocity of the same road. This makes it more difficult for the attacker to distinguish trajectory from false paths. And second, we also analyze energy consumption under different scheduling strategies where N denote the ratio between the truth queries and the false queries. Random I and sys I denote the average energy consumption result of user I when he adopt distinct or continuous scheduling strategies respectively. Here we can see that the energy consumption increased rapidly. Here is just the beginning part of our studies, and here we have proposed a mobile terminal-based trajectory preservation scheme. This scheme doesn't need additional third-party servers, and this can be implemented on a smart mobile phone terminal. This script doesn't need multiple number of users, just unlike key learning model. And our scheme achieves efficient location and trajectory protection with endurable overhead. And this is it.
So if you have further questions, please send the email offline. Thanks, speaker, one more time. The last speaker is Xiao Yutong. He's from Uppsala University. He will talk about the ubiquitous publish subscribe platform for wireless sensor networks with mobile viewers.
In recent years, we learned that the ubiquitous sensing becomes more and more popular topic. But during our research, we found that there still are some concrete problems still need to be solved before we can promote the ubiquitous sensing applications in our real life. The first one we found is in most real-life scenarios, the stationary sensors are more likely to be sparsely deployed, which means they are not interconnected with each other as we saw in traditional wireless sensor networks. As you can see from this graph, the temperature sensors are sparsely deployed across the forest. In this case, it would be cost prohibitive to connect each of the individual sensors to the internet. As a result, their deployments and usage would be heavily limited. On the other hand, applications of mobile sensors become incredibly popular. But as you can find from the figure, those applications would usually be constrained by their sensor types and abilities. Based on those considerations, we thought about building a novel platform which could solve those problems. There are two goals of our platform. The first, by using our platform, we would like to make the deployments of stationary sensors easier and more flexible. The second, we want to enable ubiquitous sensing services from stationary sensors and mobile sensors at the same time. Here is the system model we will use in our topic. Because the ubiquitous sensing system would be composed of all kinds of sensors which are distributed, highly distributed. So we choose publish-subscribe paradigm as the model we used in our platform. Second, in order to support the sparsely deployed sensor networks, we utilize smartphones as both mobile sensors and data mules. By data mules, we mean that the smartphones can communicate through short-range communications with those stationary sensors. For example, use IEEE L254, Bluetooth or not. While the mobile users carrying the mobile phone around, they may encounter the stationary sensors opportunistically. Therefore, those mobile phones can communicate with those stationary sensors opportunistically and fetch data. As I mentioned previously, the stationary sensors in our topic are considered to be sparsely deployed. So here are some 3 key challenges to build such a platform. The first one is deployments of both stationary sensors and mobile sensors could be highly dynamic, which means our platform should not rely on any specific deployments of sensor networks. Second, the communication would consume power very quickly from the embedded devices. Therefore, we should try to reduce the communication overhead in our platform. Third, the mobile users who carry the mobile phones would have uncontrollable mobility, which means that our platform should support highly opportunistic communications between different devices. Here are some existing work which are related to our topic. Those work focus on adoption of publish-subscribe paradigm in wireless sensor networks, or just enable publish-subscribe system with the mobile environment. However, they didn't consider the topic, the points we thought in our topic, such as sensing context, heterogeneity of sensing devices, mobility of those, and limited connectivity of wireless sensors. To begin, introduce you the detailed design of our platform, I will first show you the network perspective of our platform. As you can see, there are stationary sensors and mobile sensors which will act as the publishers in a publish-subscribe system. Then the internet users would act as the subscribers, which they can subscribe services provided by those sensors. And there is a broker in our system which would relay messages between internet consumers and the mobile broker. In our platform, the mobile brokers are actually the mobile phones, which will relay messages between the underlying sensors and the broker. In order to achieve high-level abstraction of from the underlying deployments of sensor networks, we designed these area-based subscriptions in our system. So for the internet users, they only need to specify the target area, their time range of interest, or service content in their subscription. With this subscription, the internet users didn't know the specific deployment detail of the underlying sensor networks. And once the broker receives the subscription from the internet users, it will try to deliver the subscriptions to mobile brokers based on their real-time locations. Then once the mobile broker receives subscriptions, it will relay those subscriptions to the remotely deployed sensors around its communication range. Therefore, the mobile broker needs to update its locations periodically to the broker. However, there is the situation that the mobile broker would be very far from any target area during its work. So in this time, the mobile broker would be not possible to deliver subscriptions to any stationary sensors. Therefore, we thought we can dynamically compute the location update intervals to reduce the unnecessary location updates. From this, as you can see from the formula, the data L would be the distance between the mobile broker and the closest target area. And the S max would be the maximum speed of the mobile broker. So This formula just implies that the mobile broker will not be possible entering any target area before data T time passed. So by employing this dynamic location updates or channeler, we can just reduce communication overhead. And for subscribed target area, it is possible that there are more than one stationary sensors could provide services which can match the subscription request. So we define the full installation here, because subscription is said to be fully installed if it has been installed on all the available stationary sensors in that target area. So we try to achieve full installation in our system. But in order to achieve that goal, there are some concrete situations to be considered. The first is that the number of mobile sensors in the target area could be higher dynamic, because the mobile users who carry the phone could enter or exit the target area at any time. And therefore, we should catch our subscriptions in the broker. Then, whenever a related or suitable mobile sensor entering that target area, a copy of the subscription will be delivered to the mobile brokers accordingly. The second is that although the stationary sensors are not mobile, it's also very hard to fully install subscriptions to those stationary sensors. Because as you can find in this graph, mobile users could only encounter partial of those stationary sensors during one trip. So we will also catch the subscriptions to stationary sensors in the broker. Then whenever a mobile broker entering the target area, those subscriptions will be delivered to mobile broker in order to maximize the full installation probability. And the third, by using this, we call this policy as the best effort subscription delivery policy. And by using this policy, we not only maximize the full installation probability of our subscription, but also we can keep the joining and the removal of underlying sensor nodes transparent for our platform. As the mobile broker travel in the target area, we also need to collect data from the stationary sensors and the mobile sensors. But for stationary sensors, because their communication with mobile brokers are opportunistic, so the data will first be cached on those stationary sensors before they can be fetched to our broker. Therefore, the mobile broker will perform a pool-based event collection during its movement. But there still have a situation that those subscription has already been installed in this target area. So in this case, the event collection operation will be unnecessary. To avoid that kind of communication overhead, we define an event collection plan which will indicate whether or not the mobile broker should perform data collection operations currently. In order to approve our design, we also do real implementations on real devices. The broker was implemented as the RESTful HTTP server. And the mobile brokers are implemented on the Android operating system. But because most of the existing mobile phones do not support IEEE L215.4 radio, so we suggest a workaround solution. As you can see, we connect we connect the T-Mobile Sky sensor to the mobile phone through the USB cable. In that case, the mobile phone could communicate with stationary sensors indirectly. And for the stationary sensor, we use Contiki operating system, and the RIME communication protocol was used for the communication, and the copy file system was used for data caching. So to test our implementation, we also developed an application called hiking trail. In this application, the hikers could the hikers would carry mobile phones while they are hiking, and they could gather in the sensing data from such as temperature, humidity, or light intensity from those stationary sensors while they pass by those sensors. At the same time, the speed of the hikers and the location of the hikers could be computed by their mobile phones. So we utilize the stationary sensors and the mobile sensors at the same time in this application. The interface, you can see the interface we implemented in this application. And with this kind of application, the users could subscribe environmental data before they decide whether or not they want to go out for hiking. And the hikers could also subscribe their own exercise data for future trading purpose. There you can see the map of our test bed city. We deployed 4 stationary sensors in the test bed. They can measure the temperature, light intensity, and humidity. And those stationary sensors are deployed along 2 sidewalks. And those pictures reflect how those stationary sensors are deployed in our test bed. Those figures show the sensing data we gathered from those stationary sensors. And we also gathered the hiker's speed from mobile sensors. And through those data, we can also gain the mobility pattern of the hikers. And we also measure the hiking frequency of the users. To reflect the network quality, we also measure the data delivery delay in our experiment. For the data which are generated into the stationary sensors, the delivery delay are mainly decided by the time, by how long it was cached on the stationary sensors. So if you relate this graph with the previous one, we can find that if the hiking trail was visited more frequently, the data will be collected more quickly from the stationary sensors. And we also showed how the speed of the hikers could impact the data throughput in stationary sensors. And during the experiment, we also found that there are some duplicated data was received in our broker. At first, we feel very strange that why there are some duplicated data was received. But after we explored our implementation, we found that because we use reliable communication between the stationary sensor and mobile brokers, so it assumed that each piece of data must be successfully transmitted. Acknowledgement package should be received by the stationary sensors. But in reality, there are times that the mobile broker received the data, but the acknowledgement package was lost. So from the point of view of the stationary sensor, the data has not been transmitted successfully. So they just retransmit the data again during next time, which caused the duplicated data in our experiment. And we also measure the effect of our adaptive location update algorithms. As you can see from this graph, this algorithm could dramatically reduce the communication overhead. So, in this project, we proposed and implemented a global publish subscribe platform for ubiquitous data access from both wireless sensors and mobile phones, without relying on any network infrastructure. And the mobile phones are utilized as mobile bureaus to relay subscriptions and publish data between the internet users and the remote sensors. And we also implemented our platform on real devices and experimented in the hiking trail application. In the future, we plan to start with the coordination among heterogeneous mobile and sensing devices to further reduce the energy consumption and the communication overhead. So that's all. Thanks.
So I have a question. In your test experiment, do you remember the energy consumption for the stationary sensors? Those are battery powered?
Yeah.
Okay.
Yes, I considered this during our design. So that's why we use the pool-based data collection policy. Because at most of the time, the stationary sensors were only listening for incoming queries. So they just sleep during most of the time. And whenever they receive the query, they just give back the data we generated. So in that way, we can conserve our energy consumption.
Do you have any idea about how long time one battery can support the node? For how long time?
Oh, wow, okay. In our experiment, we use AA batteries, and this experiment lasts for half a month. And after that experiment, the battery, I think the power of the battery was only consumed by not more than 20%. Yeah, I think it will last for at least 5 months with 2 AA batteries.
Okay. So the node in most of time in sleeping here. Sleeping mode.
Yeah, yeah.
Any further questions? If there are no further questions, let's thank the speaker one more time. This concludes the session. We will have a 15-minute break, and for the speakers in the next session, please offer the
Can you make a short announcement, please, for all the posters, or the people presenting posters outside? If you have a short presentation also for the working papers, please bring it up so that we also put it in a folder so that we do the presentations right after the last presentation of the next session. Okay? So please come here now and put your slides here in the folder so that we prepare for the demos and posters and working progress session.